Greetings and salutations, magical chemists. Let's dive into that whole equilibrium discussion as it concerns acids and bases. You may recall this back in the day in pre-AP as the very first time you were ever introduced to the idea of equilibrium. It was to describe the difference between a strong acid or base and a weak acid or base. It has to do with their equilibrium constant. A strong acid or base is something that is a product-favored dissociation, which means its K value is much, much greater than 1. This means when you put a strong acid or base in water, it will 100% ionize or dissociate and break apart. So hydrochloric acid is a classic strong acid. If you put hydrochloric acid in water, well, whatever the concentration was of your hydrochloric acid, that's the concentration of H3O plus in solution, because it dissociates 100%. Same thing, strong base like sodium hydroxide, if you put sodium hydroxide in water, the concentration of sodium hydroxide is the concentration of hydroxide, because all of it breaks apart. Because of that, strong acids and bases are also strong electrolytes. Electrolytes aren't just the propaganda they use to sell you Gatorade. Electrolytes are ions in solution that allow it to conduct electricity, which it turns out are really good if you want your heart to beat, so there's a reason to consume electrolytes, but not necessarily a good enough reason to consume strong acids or bases. Weak acids or bases, you have probably guessed, thus must be not product favored. They're reactant favored. Their K value is much, much less than 1, which means they are much less than 100% ionized in water. In fact, usually less than 1% of them will ionize when put into water. So if you take a weak acid, like say vinegar, acetic acid is a weak acid. If you put the weak acid in water, the concentrations of protons in water are going to be much less than the acid in water, because very few of it actually breaks apart, releasing the proton. Similarly true with your weak base. Well, that of course means that these weak acids and bases are weak electrolytes. They're not producing ions that can conduct electricity. And it turns out that the very vast majority of acids and bases are in fact weak acids and bases. Let's look at a couple of different ways we can represent the difference between a strong acid and a weak acid, or, strong base and a weak base, but the picture I have is of acids. So hydrochloric acid, we were talking about, strong acid. When you put that into water, notice there are no HCl's, 0 HCl's. It all breaks apart into chloride ions and hydronium ions, of course, from the protons that hooked up with water. When we write the dissociation reaction of a strong acid or base, we get a one-way arrow. If it 100% dissociates, this is not actually in equilibrium. These are the things where if you calculate the K value, they're crazy numbers. It's like in electrochem, you get like 1 times 10 to the 45th or something ridiculously enormous. So we don't even usually calculate them. We just go, it's a really big number. So we say these reactions or dissociations go to completion. So they get a single arrow. So notice, however much of your acid you have before the dissociation, after dissociation, once you've reached equilibrium is completion, 100% products. So every single molecule of your strong acid will ionize or dissociate. A weak acid, like say hydrofluoric acid, well, if you take a look at what happens when you put HF in water, most of it is still HF. There's a couple of fluoride ions floating around in there. They exist, but they're a pretty low percentage when you look at it. And in fact, it makes it look like there's more because it's hard to show you a picture that would have a representative number of molecules. But usually there'd be like maybe 1 out of 100, if not fewer. So these are the cases for our weak acids and bases that we are using our equilibrium arrow going both ways. Which is kind of funny because in a way they're really hanging out primarily with the reactants here because very few are becoming products, but that's still an equilibrium arrow. So if you looked at after the dissociation, you notice the acid is still mostly intact. It is mostly not ionized. Okay, since we're talking equilibrium, we should talk about equilibrium expressions, our K, capital K that is. Well, if it's the dissociation of a generic acid, we call it a Ka value or expression. And if it's a base, it's Kb, but it's still the same equilibrium constant expression that we've been doing since the beginning of time or, last year. So our generic acid, of course, is Ha. So in a dissociation reaction, all that means is take your acid, add it to water, and show what happens. Well, notice your water, of course, is a liquid, yummy liquids, which means it is not included in our equilibrium constant expression. But the ions that are produced are definitely included. So just like every other equilibrium constant expression, we're going to put the concentration of our products on top and the concentration of our reactants on the bottom. So I have two products. I've got my conjugate base, A-, and of course my hydronium ion, H3O+. And then only one reactant is included, the aqueous HA. Haha, that's all there is to it. So for a Kb expression, now the generic base is usually written with the B. Well, if you add a base to water, you will get B having gained a proton and hydroxide. And so, of course, water's not included, so for our Kb expression, we once again have two products on the top and our singular reactant on the bottom. And so there's our generic Kb expression. Of course, we won't be doing this always with generic things, we'll be using them for actual acids and bases, but hopefully you recognize that the format's going to be pretty much the same. Okay, so we were talking about how the vast majority of acids and bases are weak, which means there is a limited number of strong acids and strong bases, which also means you might just, you definitely have to memorize the strong acids and strong bases. In fact, if there was something you were going to do on day one of the unit that would make the rest of this slightly challenging unit easier, it would be memorizing these and practicing these, just quick flashcards. Paint them on your ceilings. You could stare at them before bed. I don't know, something. But you definitely want to know these because it is going to make this entire rest of the unit so much easier. Don't worry, I've got some tricks to help you remember them. So let's look at what they are. We've got of the 4 acids based on halogens, 3 of them are strong: hydrochloric, hydrobromic, and hydroiodic, but not hydrofluoric. So watch out for that. It turns out the HF bond is really strong. And if it's really strong, then it doesn't break easily. It doesn't donate the proton very easily. It basically is totally strongly hooked up with that proton, and it does not want to let go. Okay, nitric acid also, sulfuric, and perchloric. Notice there's no U's. Sulfurous, nitrous, perchlorous. Actually, there wouldn't be a perchlorous. It would be chlorous or hypochlorous. But none of those are strong. So there's a pattern here. The more oxygens you have, the stronger the acid. We'll talk about why that is momentarily, but it might help you remember which oxyacids are the strong ones. Luckily, strong bases, way easier to memorize. Group 1, Group 2, hooked up with hydroxide, boom, strong bases. That means if you take any of the metals from the first 2 columns of the periodic table and you add them to a hydroxide, that is going to be a strong base. So, short and sweet. Now, solubility really comes into play here. Remember KSP, it's fun. When you're really soluble, you're going to be a very strong base. Here's the thing though, beryllium hydroxide and magnesium hydroxide are in fact not very soluble. But here's the logic. We still say that they are considered strong bases because the small amount of the base that does dissolve will 100% ionize. So they're defined as strong even though they don't really dissolve, so they wouldn't be something you would want to choose if you needed a go-to strong base. Usually we stick with the alkali metal hydroxides for those. All right, so hopefully you're good on the strong bases. Let's talk about a couple of different ways you could remember the strong acids. Do you remember Brinkelhoff? Of course you do. It's the best way to remember diatomics, and it's fun to say. Well, there's an equivalent phrase for remembering the strong acids. Doesn't sound quite the same, but it is Brickel, so no clo. So it's to help you remember the bromine, iodine, and chlorine, and then you get your sulfuric, nitric, and perchloric. You have to remember how many oxygens go for each one. So this is good to remember the formula. You can even choose how you want to pronounce it depending on how you're feeling. You'd be like, Brickel so no clo, or Brickel so no clo. I don't know. Whatever works for you. So that is one way to remember. There is also, of course, a musical way to remember, especially if you know the song, You Are My Sunshine. There is, believe it or not, there's an acids version. So this is something you could also use to remember not only the names of your strong acids, but what happens to them. So this is how the song goes. All my strong acids, they share the same fate, to 100% dissociate. They will never get back together. All their H's are gone forever. There's hydrochloric and hydrobromic, and hydroiodic just says hi. Then there's perchloric, of course sulfuric, and then nitric by the by. And there you go, 2 different ways to remember your strong acids. So let's talk about that oxyacid trend. Whoops, that's not what I wanted. So for the oxyacid trend, I mentioned this briefly. The idea is the more oxygens that you have present in that polyatomic oxyacid, the stronger the acid will be within that group. This has to do with something way back in the day from periodic trends. Well, remember, in a polyatomic ion, in an oxyacid, where the hydrogen is hooked up to your polyatomic, it has an oxygen. So the hydrogen that's being donated from the acid is bonded to an oxygen atoms, and oxygen is highly electronegative. Well, if you're highly electronegative, you may have forgotten, but that means you are pulling really strongly on the bonded pair of electrons. So basically pulling them away from the hydrogen. So, if you have more oxygen atoms, you're going to have greater bond polarity. There's another word from way back in the day. So, bond polarity means that your electrons are unevenly distributed because the oxygen is basically stealing them. It's being greedy. It has more than it should. Well, that means the hydrogen has a lower electron density, which gives it a greater positive charge density. And remember, if you're an acid donating an H, you're not donating literally H, it's H+. So the greater the positive charge density around the hydrogen, it's basically practically H+ already. So it makes it easier for it finally to just break off and become just straight up H+. And of course, the easier it is to get rid of that H+, the stronger an acid you are. So if we look at remember there's the order of the strength of the acids from hypochlorous through chlorous, chloric, and perchloric. Well, remember, perchloric, this is the only one that actually shows up on the list of strong acids. There are 4 freaking oxygens around that chlorine in your perchlorate, so it's very easy to knock off that hydrogen. But when you get down to hypochlorous, there's only a singular oxygen. And it is electronegative, and it does create a bond dipole. But it's just not nearly as easy to kick off that hydrogen. Notice, this is a really dang weak acid, a very low Ka. So notice the trend is very distinctive. That's why when you're memorizing your list of strong acids, it's always the ones that have the most oxygens are the strong acids. Okay, let's talk a little bit more about Ka. This is called, another lovely name for your equilibrium constant for an acid, is called the acid ionization constant. So watch out for that phrase. It will totally show up. They'll be like, what's the ionization constant? You'll be like, what's that? It's your equilibrium constant for the acid. Well, the larger your Ka, the stronger the acid. And the size of your Ka depends on the strength of attraction between your A-, the anion that's hooked up to your H+. So the stronger that attraction, the weaker your acid will be, with a lower Ka value. But of course, if there's a weaker attraction, then it's easier to get rid of the H. You have a stronger acid. We can also talk equivalently about bases with the base ionization constant Kb. A larger Kb value will, of course, mean a stronger base. And the size of Kb depends on the attraction between your base, B, and the H+ ion. The more the base wants the proton, or the stronger the attraction, then you have a stronger base with a higher Kb value. Okay, so let's continue our journey and talk a little bit more about equilibrium and Bronsted-Lowry reactions. So generally, when we have an equilibrium system, we mean both the forward and reverse reactions are occurring. Well, when you have an acid and a base reacting together, the extent of the reaction depends on the relative strength of the acid and the base. It is important to recognize here that the stronger an acid you have, the weaker its conjugate will be, and of course, vice versa. Let's look at an example to see why that is. So we're going to look at the strong acid, hydrochloric acid. It's always a convenient one. Because it's a strong acid, this reaction goes to completion. So HCl is acting as the acid, and it donates its proton to water, which is acting as the base, forming the conjugate base, which is the chloride ion, and the conjugate acid, the hydronium ion. Now this, of course, is strong acid, so the K is much greater than 1. The products are very, very favored. Notice the arrow. It goes to completion. But let's try to reverse that reaction. Let's take chloride and, let's put it with water. That's supposed to be water. So in this case, we would have the chloride ion acting as our base and water acting as the acid, which would produce the conjugate acid, hydrochloric acid, and the conjugate base, hydroxide. Well, this is a ridiculously improbable reaction. In fact, this really doesn't even happen because remember that hydrochloric acid is a strong acid. By definition, it dissociates 100%. That means that chloride ion does not want that proton back. It's like, screw you, we're done, our relationship is over. There's never getting back together. So that's why if you've got a strong acid, its conjugate is very, very weak. Okay, something else important to note. You can tell from this example the favored direction. Remember, hydrochloric acid, strong acid, it favored the formation of products, right? We just totally agreed on that, so I hope it's totally right. So, product favored. But wait a second. Remember that hydrochloric acid is a strong acid? And we just established that the chloride ion is a really weak base. But it was the products that were favored. This is in fact always going to hold true. The favored direction of the reaction is the one in which the weaker acid and base are produced. This is so important. It's so important it got its own box. Notice also, this means that the stronger acid and base are going to be on the same side of the equation, and so will the weaker acid and base. So let's look at the type of problems you can analyze using this information. Okay. So it's always good before you do anything else in an acid-base problem, identify what's your acid, your base, and your conjugate. So take a moment to identify those lovely 4 things, and when you're ready to check your answers, unpause the video. Okay, so notice they are telling us for this example, K is much, much bigger than 1. So hopefully you realize that means this is a product-favored reaction. Well, we know if the products are favored, these must be the weaker of the 2 acids and bases. So it asks us to identify the stronger acid and the weaker acid. Well, there are 2 acids, right? There's the perchloric acid that we started with, and then there's H3O+, the conjugate acid. Clearly, the weaker acid is the one on the favored side, so H3O+ must be weaker. And perchloric is stronger. Of course it is. It's a strong acid. Now for the bases, of course, that means the weaker base is our conjugate base, perchlorate. So the stronger base here is going to be water. So that's kind of how you reason your way through a problem like this. So guess what? There's another example just for you. I am sure you're thrilled. So go ahead and try this lovely, lovely example. And when you are ready to check your answer, of course, unpause the video. Okay, well in this example, K was less than 1, so it must be reactant favored. So that means your reactants are the weaker acid and base. Once you recognize that, it's easy enough to figure out which one is going to be stronger or weaker for both the acid and the base. By the way, did you recognize this polyatomic ion? It's Chku, which is the other name, of course, for acetate. Usually we do C2H3O2-, but it can also be written like this. All right, one more practice problem. Before we actually answer the problem, we're going to go ahead and identify the conjugate base for each one of those 3 acids. So you should try that, and when you're ready to check your answer, unpause the video. Speaking of acetate, there's our acetate ion. And then I'm actually not sure what OCN- is called. And then we've got our fluoride ion. So they want you to rank the acids in order based on increasing strength And then the conjugate base is in order of increasing strength. So you should try it. It'll be fun. And then, when you're ready to check your answer, you know what to do. Okay, well, for the acids, in order of increasing strength, you had to look at their Kas. A bigger Ka was going to be stronger. So we started with the weakest one, the smallest Ka value, and then we just kept going up. And hey, look at that, they were in order already. Now, for the conjugate bases, remember that the stronger the acid, the weaker the conjugate. So this will actually have reversed the order. That's it. Okay, there's only one more problem type that you could be asked with this kind of Bronsted-Lowry expression, talking about your K values. So let's go ahead and try that. So we're just going to do the top, the very top of page 10, and that's it. You don't have to do the bottom of page 10. We'll do it in class together. So you can use, if you are given the Ka values of two different acids, you can use that to determine whether or not a given acid-base reaction is reactant or product favored. So let's take a look. Now first, we need to identify our conjugate acid-base pairs. So we need to identify what's, the acid, the base, the conjugate acid, conjugate base. So let's try that first, which makes it easy to identify the conjugate acid-base pairs. Now when we want to identify which acid is stronger, well, of course, we are just going to compare our Ka values. Well, clearly, the larger Ka value must be the stronger acid. So acetic acid is stronger. So now, if we want to know if this example reaction is reactant or product favored, well, remember, it favors the weak. It's like the opposite of evolution. So if acetic acid is stronger, that means your carbonic acid, H2CO3, must be weaker. And since this one is weaker, it must be product favored. And once you know it's product favored, then it's easy to tell the K value must be greater than 1. And that's about as complicated as it's going to get, at least for identifying equilibrium Bronsted-Lowry reversible reactions. So we are good to go. You are ready for the very first day and the glories of acids and bases. I'll see you there.